Welcome everyone to our video on VSEPR theory and molecular geometry, in which we'll look at the different shapes that molecules can take on. Now the molecule I have in front of me is vitamin D3. This is a complex molecule. If we start to look at it, we see rings and double bonds, and the shape seems incredibly difficult to figure out. How could we possibly know how a molecule like this would take on the shape that it does? However, when you start to look at the individual carbon atoms, these black circle spheres here, we see that the shape around each individual carbon atom is very similar. We see carbon atoms with 4 atoms that they're bonded to, and then we see some carbon atoms with 3 atoms that they're bonded to. And the ones with 3 atoms that they have bonded to all have very similar shapes. And we keep seeing these patterns as we look at this complex molecule. And this is the beauty of chemistry, that these incredibly complex organic molecules are built upon these building block shapes. And those are the shapes that we're going to consider today. The basic shapes in chemistry that make up all molecular structures. Our learning goals for today are to introduce VSEPR theory, to describe the shapes of molecules which have 2, 3, or 4 pairs of valence electrons around the central atom, and we will also visualize these shapes in 3 dimensions. Going into this video, you should know how covalent bonding works and need to use the Lewis theory of bonding to go from a molecular formula to draw a Lewis structure. VSEPR theory stands for valence shell electron pair repulsion theory. This theory states that the shape of the molecule will be such that the valence electrons will minimize electron-electron repulsion. When we talk about valence electrons, we are going to be using 2 pieces of terminology. We're going to be talking about bonding pairs. So a bonding pair is 2 electrons in a covalent bond, and a double bond would be 2 bonding pairs, so a total of 4 electrons. And then we'll also be referring to lone pairs. Lone pairs are electrons belonging only to one of the atoms making up its valence shell. The valence shells that are going to be important for minimizing repulsion are the bonding pairs and the lone pairs on the central atom. Another piece of terminology we will be using is the steric number. The steric number is a count of the total number of valence electron pairs around the central atom, which is simply the bonding pairs plus the lone pairs. Before getting into the shapes of molecules, we are going to look at how those electron pairs around the central atom will arrange themselves to minimize repulsion. This arrangement is referred to as the electron or electronic geometry. After considering the way the electrons will arrange themselves, we'll start adding atoms around that central atom and look at the shapes of actual molecules, which are simply based upon the electronic geometry. Let's first take an example of how to minimize the repulsion around the central atom by considering a central atom with a total of 2 electron pairs. We're going to visualize the shapes that molecules form using a simulation from the website PHET, P-H-E-T. It's run by the University of Colorado and it has some great chemistry and physics simulations. If you want to look at this, this is the molecular shapes simulation. So just Google search PHET, P-H-E-T, molecular shapes, and you'll be able to find the simulation fairly easily. What we're going to consider right now is the shape that the electron pairs will take on around the central atom to minimize repulsion. So here's my central atom in purple, and now I'm going to add a lone pair of electrons. We see the pair of electrons there, and the shape there represents the electron cloud. Our first shape here is going to be when we have two lone pairs of electrons about the central atom. We see that when we have two pairs of electrons, they'll arrange themselves on either side of that atom, forming a straight line from one electron pair to the central atom to the other electron pair. This is referred to as a linear shape, and there is 180 degrees between those two electron pairs. So we've seen that in order to minimize repulsion when there are only two pairs of electrons around the central atom, the electrons will form a linear shape, or there will be 180 degrees between those electron pairs. In our second example here, we are going to consider an example where we have a central atom with three pairs of electrons. Here I have the two electron pairs, and let's add one more now. When we have three electron pairs, they arrange themselves in what looks to be a triangle. I'll move this around so we can see it like this. So we see them spread out equally in a triangle, and if I move the molecule here, you can see that they're all in the same plane. Okay, so this is a two-dimensional shape because they're only in one plane. This shape here is referred to as trigonal planar, a triangle in a plane. When the central atom has a total of three pairs of electrons, to minimize repulsion, those electrons will form a trigonal planar shape with 120 degrees between each of the electron pairs. Finally, let's look at the example when we have four pairs of electrons about the central atom. Now we're going to move on to four electron pairs. In order to minimize repulsion when we have four electron pairs, we have this shape that's referred to as tetrahedral. So now we have truly a three-dimensional shape. One thing to note is that all four of these electron pairs are spaced out equally in 3 dimensions. So no matter which way I rotate this shape here, it's symmetrical in all sides here. So this is a tetrahedral shape, and there is 109.5 degrees between each of those electron pairs. So now we've reached our first 3-dimensional shape. Now that we have four pairs of electrons, they must arrange themselves not in a single plane, but in 3 dimensions. And that shape was what's referred to as a tetrahedral shape, where there's 109.5 degrees between electrons pairs. Let's now go back and look at actual molecules and learn about the shapes that different molecules form when we actually add atoms and bonds onto those electron pairs. Let's start off with our atom here with 2 pairs of electrons. They form that linear shape, and let's just replace those with bonded pairs. It takes on the same shape. This shape is also referred to as linear. They form a straight line with 180 degrees between the bonds. When the central atom has 2 pairs of electrons, and both of those pairs are bonded pairs, the molecule shape is a linear shape. The 3 atoms that form the molecule are in a straight line, and there's 180 degrees between the bonds. For our next shape here, we are looking at 3 bonded pairs and no lone pairs. Just like with our previous example, when we have 3 bonded pairs and no lone pairs, the shape that the molecule takes on is the same arrangement as the electron pairs themselves, because we've replaced each electron pair with a bonded pair. Between each of these bonds is 120 degrees, and the shape is once again trigonal planar. We have a triangle in a plane. When we have 3 bonded pairs and no lone pairs around the central atom, the molecular shape is referred to as trigonal planar. All 4 of the atoms in the molecule lie in one plane, And you can picture the terminal atoms forming a triangle. The angle between the bonds is 120 degrees. I'm now going to replace one of those bonded pairs with a lone pair. So still 3 pairs of electrons, but one of those 3 is a lone pair. So we see that the 3 pairs of electrons still make that trigonoplanar shape. However, the shape of the molecule itself is this V shape or bent shape. If we now take one of those bonded pairs and have a lone pair instead, so still 3 total pairs, but only 2 of them are bonded, we see that the molecule itself forms a bent shape, kind of shaped like a V. The angle between the bonds is going to be slightly less than 120 degrees, and that's because the lone pair is causing more repulsion, pushing the bonds a bit closer together. Now we're moving on to 4 pairs of electrons. If all those 4 pairs are bonded pairs, we have this tetrahedral shape with 109.5 degrees between each of the bonds. Remember, this is a symmetrical shape, so no matter which way I turn it, it looks the same in all directions. When a molecule consists of a central atom and 4 bonded pairs about that central atom, this is a tetrahedral shape where there's 109.5 degrees between each of those bonds. Let's now consider a case where one of those 4 pairs of electrons is a lone pair. So the 4 pairs of electrons still arrange themselves in that tetrahedral-based shape, but now the shape of the actual molecule, and I'm going to hide the lone pair, is now this trigonopyramidal shape. So the central atoms sitting at the top of the pyramid, the apex of the pyramid, and then the 3 legs of the pyramid are the 3 bonded pairs. If we look at this from up top, we'll see that triangle where all of those 3 legs are equally spaced apart. When we have 4 pairs of electrons about the central atom, but one of those 4 pairs is a lone pair, the molecule itself takes on a pyramidal shape, where the base of that pyramid is a triangle. So it's trigonal, pyramidal. The angle between those bonds is slightly below 109.5 that we see in the tetrahedral, and that's because that lone pair is causing more repulsion and pushing those bonded pairs closer together. Finally, let us replace another bonded pair with a lone pair. Once again, the 4 electron pairs around the central atom take on that tetrahedral shape, but if we look at the molecule itself and hide the lone pairs, we see that the molecule takes on a bent shape. This is the shape of water, where the oxygen molecule has 4 pairs of electrons, 2 lone pairs, and 2 bonded pairs. If we have 4 pairs of electrons about the central atom, but now 2 of them are lone pairs, this is an example like water, the molecular shape is referred to as bent, or sometimes referred to as linear bent. The angle between the bonds is now decreased even further from 109.5, and that's because we have 2 lone pairs causing even more repulsion, pushing the bonded pairs closer together. Using water as an example, water's bonds are about 104, 105 degrees apart, so we've decreased the angle even further from the idealized tetrahedral shape, 109.5. So those are the shapes going up to steric number 4. Tune into the next part of this video to look at molecules that form with steric number 5 and steric number 6.